chapter 1, which is introduction, we have four main parts. The first part is methanol introduction. Methanol is known as methyl alcohol and it is the simplest alcohol compound. Also, the molecular formula is CH3OH. Methanol can be also known as carbinol. It has no taste, no color, a slight scent, and it is flammable. For the market analysis of methanol, methanol showed a CAGR of 5.64%. Why? Because the main factor is that the demand for methanol-based fuel in China is really high. They already have 5,000 cabs that run on methanol instead of fuel. Methanex, Savage, and Petronas are some of the big companies in this field. For the proposal of suitable plant capacity, we picked a number of 2,500 metric tons daily with astronaut technology. We found that if we went beyond this, then two-step reforming would be required instead. For the instrument selection for methanol production process, there are 5 main process units and some supporting units. All of these units can be shown in the process flow diagram, which will be explained by Gladys. For the supporting units, their role is to adjust the temperature and pressure accordingly to accommodate for the feed condition. Now, for the executive summary part, we will be discussing about the methanol production process in this project. That's the main thing. And then we have 3 steps involved: the production of syngas, methanol synthesis, distillation process. Finally, we obtain methanol as a product of purity 99.5.
This is the process flow diagram of our methanol production plant. To produce methanol, firstly, desulfurized methane is mixed with excess steam and is reacted in the reforming reactor at given temperature and pressure with the presence of cobalt as catalyst to produce syngas. Then, 95% of the excess steam is removed through the condenser, and after compressing the syngas stream to the desired temperature and pressure range, it is then reacted in the methanol reactor with the presence of copper zinc oxide with aluminum oxide catalyst to produce methanol. In the syngas recovery unit, unreacted syngas is recovered as overhead product and 90% of the stream is recycled, while the bottom product yields methanol and water. The methanol is further purified in methanol purification unit at the pressure between 2 to 4 bar to finally obtain 95% purity of methanol. Next, this is the overall block diagram and summary of stream composition of the methanol plant. Based on the capacity of the methanol production, which is 2,500 metric ton of methanol per day, a back calculation starting from the methanol purification unit is made to determine the other unknown compositions of the plant. These are the general assumptions that is made during the calculation of the mass balance. The overall mass balance of the plant yield an error of 0.09%, and based on our design of the plant, approximately 70,000 kg per hour of methane and 120,000 kg per hour of excess steam is needed to produce 2,500 metric ton of methanol per day with 95% purity.
This is our chemical engineering thermodynamics part. Part A, vapor-liquid equilibrium. What we have here is Hi6 X and Y graph, vapor-liquid equilibrium XY data for a binary mixture of methanol and water at temperature 66 degrees Celsius. As methanol liquid phase mole fraction X increases, methanol's vapor phase mole fraction increases as well. This means that X and Y are directionally proportional. The graph also shows that methanol's vapor phase mole fraction Y is higher than methanol's liquid phase mole fraction X. The cause of this is that methanol is much more volatile than water. If we compare it to the experimental data VLE graph, which holds the data for methanol-water binary mixture at temperature 49.76 degrees Celsius, the same trend can be observed. X and Y are directionally proportional to each other. X increases as Y increases. However, in the experimental data, methanol's liquid phase mole fraction does not increase linearly as opposed to the one in the Hi6 graph. Methanol's experimental vapor phase mole fraction maintains an almost same trend with the Hi6 graph. For the Hi6 P versus XY graph, which holds the data for methanol-water mixture at temperature 66 degrees Celsius, It is observed that the bubble curve increases a bit more linearly as opposed to the dew curve, which increases in a more exponentially trend. The bubble curve is also observed to be higher than the dew curve. This is because the bubble point of methanol water mixture is higher than its dew point. Comparing it to the experimental data for methanol water mixture at temperature 49.76 degrees Celsius, the same trend can be observed. The bubble curve increases somewhat linearly and the dew curve increases in an exponential trend. The bubble point is also observed to be above the dew curve. Therefore, the same conclusion can be made. The bubble point of methanol water mixture is higher than its dew point. Part B. Phase envelope. As you can see from the table, at temperature 66 degrees Celsius, the mole fraction of water and methanol in stream 10 are 0.8762 and 0.1238 respectively. Since the composition of the mixture in stream 10 consists about 80% of methanol, hence the physical properties of the mixture in stream 10 is mainly influenced by that of methanol. In the P versus T graph, besides here, we can observe that both dew point line and bubble point line are similar and produce a single curved line graph instead of two curved line graphs joined at both ends. This is caused by the high content of methanol molecules in the mixture compared to water molecules. In the phase envelope section, other graphs such as PT versus VHS graphs are shown. The bubble point on this graph is represented with red lines and the dew points are represented with blue lines, unlike the P versus T graph. The specific volume, specific enthalpy, and specific entropy can be obtained easily at dew and bubble points from these graphs.
Greetings, my name is Jeremy Wilson and I will be presenting Chapter 3 Part C, which is flash calculation using Aspen HYSYS. The objective of my part is to solve and predict the mole fraction of vapor over liquid as well as the composition in S3 using Aspen HYSYS, as well as to calculate the percentage of water removal. In order to achieve the objective, a simulation diagram of the condenser is first designed, where it comprises of a compressor to increase the pressure and a cooler to decrease the temperature. The condition of stream 3 is at an initial pressure of 1000 kPa, while an initial temperature of 100 degrees Celsius, while the final pressure at stream 3B, which exits the cooler, is at a pressure of 6500 kPa and a final temperature of 95 degrees Celsius. The molar flow rate of S3, which is stated here, can be acquired from the process flow diagram, and the basis behind our initial conditions for stream 3 is through literature review. These are the properties of stream 3 used in the Fang-Robinson cubic equation to simulate our conditions of streams involved with the separator. As it can be seen over here, is that the temperature and pressure is at a constant of 95 degrees Celsius and 6500 kilopascal. And these are the compositions of the stream with the separator, which is later used in order to calculate the water of percentage removal. We've calculated the percentage of water removal using this formula below, where we can say that approximately 95% of water is removed. That is all.
Good day to our respected lecturers. In order to obtain the number of theoretical stages required, we started off with the calculation of the saturation pressure. Since our system falls within the temperature range, which is 66 degrees Celsius, we are going to use Antoine equation to compute the saturation pressure for both methanol and water. We are going to get 106.62 kilopascal and 26.24 kilopascal of saturation pressure for both methanol and water respectively. So by taking the value of saturation pressure for methanol and water, we calculate the relative volatility of methanol with respect to B by assuming our system follows the Raoult's law. So we are going to get our relative volatility equal to 4.0633. Use the value of relative volatility that we got to compute our equilibrium curve equation. Take 6 trial and error values for x to compute our y values. To plot our equilibrium curve, plot all the trial and error values that we calculate previously, connect them with each other, and then we will get a curve like this. Starting from the origin, draw a 45-degree line. Plot the composition of the methanol on the feed stream, as well as at the bottom and then distillate stream on the x-axis. And then we take all these 3 points and then draw three vertical lines until it touches the 45-degree line. Use the flash calculation to calculate the Q value. By taking 0.94 from the table B2 in the question, we are going to get L 0.06, which is also equal to Q. And then we substitute this Q value to the feed line equation, which is this one. And then we are going to get Y equal to negative 0.0638x plus 0.932. Similarly, we are going to take two trial and error point for x, plot these 2 points on our graph, and then connect them with straight lines. Now we need to draw an enriching line. Take this point, make a straight line all the way to y-axis. Intersection of these 3 points here, we are going to get 0.66 and 0.89. That is the value of our x prime and y prime. To substitute them to this equation, get our reflux minimum value, which is 0.1061. Since optimum operating reflux ratio falls within this range, we are going to plot 4 graphs to make sure that we get the least number of stages. To do so, we are going to calculate the enriching lines for 1.2 R mean all the way to 1.5 R mean. Take 2 values of trial and error x point to compute our x. For reflux ratio equal to 1.2 R mean, this is how our graph is supposed to look like. We take these 2 values of x 0 and y 0.8111 and x 0.6 and y 0.8788. Plot that value on our graph and then connect them together to make a straight line. So we are going to get our enriching line like this. Get the intersection point of our enriching line and feed line. To take this point and make a straight line all the way to this point. So this is our stripping line. From this point, we are going to make a horizontal line until it touches our equilibrium line. So from this point, draw another vertical line down until it touches our enriching line here. From here, we are going to repeat the same process as we did earlier until this horizontal line passes over this point. For the R1.2 R mean, we have a reminder of 0.3 stages. Overall, we get 3.3 stages, including the reboiler stage. Repeat the same process for R equal to 1.3 R mean until R equal to 1.5 R mean. After plotting all 4 graphs, we came up with the conclusion of 2.3 number of theoretical trace minus the reboiler with our optimum reflux ratio of 1.2 R mean.